Inner product, length, orthogonality. This is from 6.1 and 6.2. We first define inner product. So we have U and V, both are from n-dimensional column vector. Now we can define operator dot or inner product. So U dot V is equal to U transpose V. So because U and V both are given as column vectors, so U transpose is row vector. So U is like this, V is look like this. In other words, this can be written as summation of first component times first component, second component times second component, all the way down there, U and V. Now we can define the length of a given vector V, n-dimensional vector, which can be written as, defined as, so we used double line, vertical lines to denote that length. So this can be computed from square root of V dot V, V inner product V. So if you write V dot V, then it is V1 square plus V all the way Vn square. So basically this is square root of sum of squares. There are a few properties. There's no surprise for those properties because those are just common for scalar products. So given three n-dimensional vectors, column vectors, then U dot V is equal to V dot U, so commutativity and distributive law. And if you have scalar multiplication to U before dot, then you can actually take out this constant scalar. And U dot U, which is basically the length U square, is always greater than or equal to 0, because this is squared. Square of a number is always greater than or equal to 0. And U dot U equals 0. In other words, the length is 0 if and only if the vector is given as 0. Vector normalization. If the length of a vector is 1, then this vector is called unit vector. Or you can say direction. So those are equivalent terminologies. A vector can be written as the product of its length and direction. So what it means is, if you're given a vector V, n-dimensional vector V, then first you can calculate its length, and it can be multiplied to the vector divided by the length. So basically this is just length multiplied by direction. Find a vector A that has the same direction as negative 6, 7, 6 with length 5. So for this problem, we first want to find length and then direction of this vector, and then we will see how to rescale that as length 5. So V is given by negative 6, 7, 6. Then what is the length? The length is square root of sum of squares. So this is 121, 11 square. So this is 11. Then we know that the normalization of V, or direction, is V divided by its length. So this is 1 over 11, negative 676. This is length. If you divide the vector by length, then this is unit vector or direction. Then the question asks for the same direction with length 5. Then what you do is just multiply by 5. So if you want to say u is the vector with length 5, then 5 times the direction, unit vector, which is 5 over 11, negative 676. Orthogonality. Orthogonality means 90-degree vectors. So if u and v is said to be orthogonal or perpendicular, if u and v are perpendicular, so 90 degrees. And Pythagorean says if u is orthogonal to v, then u square, u length square plus v length square equals u minus v square. Or equivalent to u dot v equals 0. All right, we need a little bit of explanation for this. So u perpendicular to v, then we can think of two vectors in 2 dimensions. And Pythagorean theorem usually tells us if you form a right triangle, then this square plus this square equals, so the sum of two squares of right size is equal to the square of the hypotenuse. So this guy is u, this guy is v, the length is u, the length up here is v, but the hypotenuse is the length of u minus v. So Pythagorean basically tells you u square plus v square equals u minus v square. And now we can do a little bit more calculation from here. So u square plus v square, and this means u minus v, so inner product of u minus v, u minus v dot u minus v. And we can expand this by distribution law. So u dot u is u square, and then here is v dot u and u dot v, so that is u 2 times u dot v, and then the last one is plus v square. So the right hand side and the left hand side cancelled out with 2 terms, so we have negative 2u dot v. That means from perpendicular properties, we can equivalently obtain their inner product equals 0. So if uv is said to be orthogonal, you can say if u dot v equals 0. Orthogonal set. So if this is exactly what we have derived, so u perpendicular to v if and only if u dot v equals 0. Now if you have a set of vectors, maybe more than 3, the set is called orthogonal if each pair of these vectors is orthogonal to each other. An orthogonal set of vectors is called orthonormal. So orthonormal if each vector has unit length. So orthonormal requires orthogonality of these vectors and unit length. Now the last example, let's look at three vectors given here, and is it orthogonal set? To verify that, to check if this is orthogonal set, we actually need three computations. So first I want to look at U1, U2, this pair. Is this 0? From here, U1 dot U2 is -3 multiplied plus 2 plus 1. So this is 0. So we're done. But this is not the only condition. We need U1 U dot 3 is at 0 and U2 U dot 3 is at 0. So we need to check each pair for its orthogonality. So U2 U3 is -1 -1 is 1, -8 7. So this is 0. So this is yes. And U2 U3. So everything can be checked if you multiply U1 U3. So 3 times -1, -3, -4, 7. Now the second question is find the length of each vector. For the length, so U1 length is square root of 3 square, 1 square, 1 square, so the 11. And U2 is -1 square, 2 square plus 1 square, which is 6. And U3 is -1 square, 4 square, 7 square, which is 50, 66. Now, next question is it orthonormal set? Of course, it's not an orthonormal set. They are orthogonal to each other, but their length is not normalized or is not unit. So to get orthonormal set, what you do is you want to divide each vector by its length. So we can do U1 hat as square root of 11, 3, 1, 1. This is the same thing as you put square root of 11 to each denominator. So they are equivalent. It's up to you. And U2 is also the same. U3 is also the same after normalization. So you need to divide the length for each edge of that vector. So to get orthonormal set. All right, we're going to stop here.